Hello, ladies and gentlemen. Perfect timing for me to start my video right on the bell. Anyway, this is your daily dose of Dorfler here. Before we get into today's discussion, I have already made changes to the plan for the rest of the semester. Originally, I intended on doing section 2 as kind of one video, but there's a lot in this video. So I decided to go ahead and split it into 2 shorter videos. I know that'll make some of you happy. So take a look at Plan Book and see the minor changes I've made. Basically, today and tomorrow we'll be working on section 2. And then on Friday will be section 3. I have bumped the quiz and the due date for the 3 sections of problem sets to Tuesday. So it's no longer Monday. So it's been bumped to Tuesday. On Monday the 7th, you are to continue or finish. You are to finish working on the neutralization worksheet that I'm going to give you on Friday after section 3 is done. And then I'm going to try to be on Google Meets during your regular class times on Monday the 7th in case you have any questions, okay? So that's kind of how we're going to roll here, which right now it works out fine. We don't have a whole lot more wiggle room to deal with. So we're going to be cutting it real close. Right now we're still good. We still have a day buffer before the break. So I'm not going to try to change too much more in terms of the schedule. Anyway, if I do, I will keep you up to date. Let's begin, shall we? So, in the first section, we talked about what we're going to be discussing in this chapter. Basically, solution chemistry. And we're going to be looking at things that happen in aqueous solutions in liquid environments. And we're going to be focusing today on what are called precipitation reactions. And it's a bummer because this was actually going to be our lab that we're going to do where we mix various solutions together to see if we're going to have a precipitation occur. And really a precipitate is when we have a reaction occur and we have the shuffling around of components to form new products. Sometimes we get a product that is not soluble. We talked about in section 1 where we have some products are going to be, or some substances are going to be soluble, meaning they can, dissolve or dissociate in water. Times that we have products made that are not soluble, we have what's called a precipitate, or essentially a solid that has formed. And it is not soluble in water. So it's kind of like when you have sand in water where sand doesn't necessarily dissolve in water. Okay, that's kind of what's going on here. So precipitation reactions when one mixes ions that form compounds that are insoluble, as could be predicted by what are called solubility guidelines. And we're going to talk about solubility guidelines in just a moment. You are, I guess you're lucky this year because in years past I've made students kind of memorize these. Obviously this year I'm not going to make you do that. So lucky you, lucky day. So let's look at the solubility guidelines. This is table 4.1, I believe, in your textbook. I know it says table 4.1, but I feel like this chapter kind of got a little wonky with those. Anyway, this table is split into 2 parts. We've got soluble ionic compounds and insoluble ionic compounds. Now, these are just an example of some substances that that can be both soluble and insoluble depending on what they bond with. Okay, so let's concentrate our attention to the top half of this table. Okay, these are soluble ionic compounds. Okay, so if we have a compound containing nitrate, acetate, chloride, bromide, iodine, or sulfate ions, typically they're going to be soluble. Okay, however, there's going to be times that substances that contain these anions, again, that's our focus here is the anions, sometimes when these anions bond with certain cations, they become insoluble. So again, normally these anions are soluble. Okay. However, if they bond with certain cations, they become insoluble. So let's just look. Nitrate and acetate, there are no what are called important exceptions. Okay. Any compound that has nitrate or acetate is going to be soluble. They just wanted to throw that in there with you. However, chlorine, bromine, iodine, sulfate, if they are bonded with certain cations, they're going to become insoluble. And if you notice, chloride, bromide, and iodide, if they are bonded with basically any of the three same cations, silver, mercury, or lead-2, okay, then they become insoluble. Sulfate is strontium, barium, mercury, and lead-2 as well. So anytime these anions are bonded with these cations, we will get an insoluble substance. And we can use, what's important about these solubility guidelines is we can use these guidelines to help predict what we should get from a reaction without actually having to do the reaction itself, okay? Then in the bottom half, we have insoluble ionic compounds. Now, this involves sulfide, carbonate, phosphate, and hydroxide. Basically, what this says is any compounds containing these four anions will be insoluble unless they are bonded with these substances, which then they will be soluble. You following along here? Okay. 1 second here, folks. I got someone needing to talk to me. Sorry about that, folks. Time to get back into it. I was trying to see what they wanted. Anyway, we're back at the solubility guidelines here. And again, before we get interrupted, we saw that down here at the bottom, if, for instance, if we have sulfide anions combining with ammonium, any alkali metals, again, those are from group 1, or those from group 2, like calcium, strontium, and barium. If sulfide is combined with any of these 4 types of cations, it then becomes soluble. Okay? See, all these listed in here, anytime you have ammonium or alkali metals, they're going to be soluble if they bond with them. With hydroxide and sulfide, if you add calcium, strontium, or barium to them, they will also become soluble. So let's take a look at some examples here. So up here in the sample exercise, we are to classify these ionic compounds as either soluble or insoluble in water. Okay, so we have sodium carbonate. So again, let's first shift our focus onto the anion, carbonate. Okay, going back to the table here. Okay, find carbonate on here. Okay, carbonate is in the portion where it's insoluble. Okay, but we then look at its cation. It's bonded with sodium. Okay, so carbonate is typically insoluble unless it is bonded with either ammonium or alkali metal cations. Well, sodium is an alkali metal. So therefore, sodium carbonate is soluble in water. Okay? Okay, carbonate, not so much, but it is bonded with an alkali metal. A-OK, makes it soluble. Lead-2 sulfate. Okay? So again, the lead-2 is very important. So let's find sulfate. Again, that's our first thing to look at. Okay, sulfate is in the portion where it is typically soluble. But we see here that exceptions to making it soluble is when it's lead-2. So since sulfate is bonded to lead-2, it becomes insoluble. Okay? So lead-2 makes sulfate insoluble. Let's look at another example. Okay. Oops, nope, I want to go back in here and I want to do this. So A and B and C. And these, it's been a while since I've written on here. So practice exercise here, again, using the solubility guidelines. classify the following compounds as either soluble or insoluble in water. So cobalt 2 hydroxide. Okay, so we shift our attention to hydroxide. Okay, maybe. Hello. Okay, sorry. So hydroxide is down here with the insoluble compounds. Okay, hydroxide becomes soluble when it's bonded with either ammonium, alkali metals, or calcium, strontium, or barium. Okay, this does not want to. Okay, so here, cobalt hydroxide. So, again, hydroxide said it's insoluble, okay? And it is bonded to cobalt. Cobalt 2, to be more specific. So, cobalt 2 is not in the exceptions. So, cobalt 2 hydroxide, maybe I think this is what's happening. Okay. Cobalt 2 hydroxide is insoluble. Okay. Barium nitrate. Okay. Nitrate is our attention here, right here. And it says there are no exceptions. So nitrate, no matter what compound it's in, is soluble. So B is soluble. And lastly, ammonium phosphate. Okay, ammonium and phosphate. Let's find phosphate first. Phosphate, PO43-, says it is insoluble unless it is bonded with ammonium, right here. So that means for ammonium phosphate that it will be soluble. Okay, so A is insoluble because cobalt 2 hydroxide does not meet the exceptions, so therefore it's insoluble. For B, barium nitrate, nitrate is soluble no matter what is bonded to it. In ammonium phosphate, phosphate is typically insoluble unless it is bonded with cations like ammonium. Therefore, it is soluble. So that's how we use the guidelines, the solubility guidelines, to determine, what will be soluble and what will be insoluble. So will we have a precipitate formed, or will it just remain a liquid state? Okay. Eventually, I'm going to get this all erased before advancing to the second portion of today's video. And done. Okay. So, the second portion of today's video is talking about metathesis reactions. Another name for metathesis reactions is called exchange reactions. That exchange is important. It comes from, metathesis does, from the Greek word that means to transpose. When we have a reaction, it appears as though the ions in the reactant compounds are going to exchange or transpose ions. I like to call this type of reaction a do-si-do reaction. Do you know what a do-si-do is? I really hope you do. Well, if you don't know, a do-si-do is like what you hear in the old time, like dances, like country dances, where do-si-do and turn your switch your partner around and around. Okay, this is what I call a do-si-do. The ions in these compounds that are reactants, they're going to do-si-do. They're essentially going to switch partners. Silver is here. We have silver nitrate in aqueous state is going to react with potassium chloride, also in its aqueous state. Okay. When they react, this silver ion here is going to do and join up with chlorine ions, and the potassium is going to switch partners and join up with the nitrate. And when you do this, you have to go all the way back to chapter 2. You have to be able to identify the charges, because when you separate them or dissociate them, they go back to their typical ionic charges. And when you whoop them, you do, you've got to do the appropriate formula. So here we get silver chloride and potassium nitrate. And so based off of our solubility guidelines, you'll see that chlorine is typically soluble unless it's bonded with silver. So we get silver chloride as a solid. That is our precipitate. Nitrate is bonded with potassium, and anything that bonds with nitrate is going to be soluble. So that stays aqueous, okay? So when we do these types of reactions, now I said way back in chapter 2 that we're not going to, at that point, have to worry about whether or not something's a solid, a gas, aqueous, liquid, or anything like that. Again, there is a difference between aqueous and liquid, right? Now, and I said we're going to have to in the not so distant future. Well, that not so distant future is right now. It's very helpful and almost necessary for you to identify each substance in a reaction as either being a solid, liquid, gas, or aqueous solution, okay? If we are to understand the reactivity, we must be aware of what is changing during the course of a reaction, okay? Now, excuse me. As this section of chapter 4 proceeds, we first get to look at a molecular equation. So we're first going to be working through these metathesis reactions, okay? The second part of this video, which you're going to see tomorrow, is going to focus on what's called a net ionic reaction. And that really means is we're going to take these molecular equations, break them up into their individual parts or individual ions for everything that can be separated, and we're going to identify the players or the ions that are actually being active in the reaction. So that's why I kind of wanted to split this up into two, okay? 2 videos. So let's look at a sample exercise here. We are predicting a metathesis reaction. Okay, so predict the identity of the precipitate that forms when aqueous solutions of barium chloride and potassium sulfate are mixed. We are then to write a balanced chemical equation for the reaction. Okay, so we are told that aqueous, if you follow me down here, aqueous barium chloride and aqueous potassium sulfate are going to bond. Okay, well, or when, I didn't say bond, I mean react. When they react, they do. So the cations switch partners, okay? So potassium is going to go join chlorine, and barium is going to go join sulfate, okay? And so we get barium sulfate and potassium chloride. And so we don't have to run this reaction. We can use the solubility guidelines to help us predict that sulfate, when bonded with barium, is going to cause it to become insoluble. So that becomes a solid. Potassium chloride is going to remain aqueous based again off of, based off of the solubility guidelines. So again, pay attention to the charges when they do, when you switch partners here, switch cations and anions. Barium is 2+, sulfate is 2-, no subscripts. Potassium is +1, chloride is -1, no subscripts. But you notice we had to add a coefficient of 2 in front of the potassium chloride because the potassium and chlorine in the reactant side had 2. So we have to make sure we balance them. Let's do a practice here. So part A says, what compound precipitates when aqueous solutions of iron 3 sulfate and lithium hydroxide are mixed? Write a balanced equation for the reaction. We'll do part C after we do A and B, because A and B go together, okay? So we'll come back to that. And I need to go to, my Okio game was not set up. What? Oh no, my OkioCam is not set up right. Let's hold on 1 second. All right, folks, we had a little bit of a technical issue here. My program that allows me to do this type of setup does not like it when another program, the program that I'm using to record, is already open. It just gets a little angry. So anyway, sorry about that. I'm gonna hope that this works, where I can combine videos. I think I can, but we'll see. Anyway, back at this. What compound precipitates when aqueous solutions of iron 3 sulfate and lithium hydroxide are mixed, and write a balanced equation for the reaction? Okay, well, first thing, let's write down what we have here. Okay, we have Fe2SO43 and we have LiOH. Okay. That's what is reacting here, okay? We need to predict what the products are going to be. You know what? I'm going to rewrite this. Hold on. I'm going to write it to where I can then go into part B. So we have Fe2 parentheses SO4 3, and it is aqueous. So I put an AQ there. Plus LiOH. It is also aqueous. They are going to yield the products. Let's think about this. So lithium and iron are the cations. They're going to switch partners. So lithium is going to go and join sulfate. Now remember, lithium is a +1, sulfate is a -2. So when you do this, you're going to get Li2SO4. Okay, I'm not going to identify the species yet because I need to write down my second product. Okay, so since lithium went with sulfate, iron has to go with hydroxide. And again, it's iron 3 because we see this subscript of 3 on the sulfate. So iron 3 plus, and hydroxide is a -1. We go oops, oops, and we get product just right there, Fe parentheses OH close parentheses 3. So let's identify what's what. Okay, we're going to go back into these solubility guidelines. Okay, so here we have Li2SO4. So sulfate right here, it is typically soluble unless it's with strontium, barium, mercury, or lead 2. But in our reaction, sulfate bonds with lithium. So that means that lithium sulfate is going to be aqueous, AQ. You can read that, AQ. Okay? Now, it doesn't automatically mean that iron 3 hydroxide is going to be a precipitate, but we can always go back and check. Okay, hydroxide is typically insoluble unless bonded with ammonium, alkali metals, calcium, strontium, or barium. In this case, hydroxide is not bonded to any of those. So that means that iron 3 hydroxide is going to be the solid or the precipitate. Okay, so that's that's answer to A. Okay, this iron 3 hydroxide is our precipitate. Next thing we need to do is balance this. Now, if you want to pause this and try to test your balancing skills, go right ahead. I'm going to show you the coefficients that belong in this reaction. Okay, so we should have a coefficient of 6 in front of the lithium hydroxide, a coefficient of 2 in front of the lithium sulfate. I'm sorry, nope, I had that backwards. I was looking at the wrong one. My bad. A coefficient of 3 in front of the lithium sulfate, and a coefficient of 2 in front of the iron 3 hydroxide. So a 6 in front of the lithium hydroxide on the reactant, a 3 in front of the lithium sulfate, and a 2 in front of the iron 3 hydroxide, which is our precipitate. Okay? Now for part C, so that answers part B. For part C, got to go back to this. Will a precipitate form when solutions of barium nitrate and potassium hydroxide are mixed? So we don't necessarily have to do a balanced equation per se. So barium nitrate and potassium hydroxide, okay? So we don't have to do there we go, a balanced chemical equation. We just have to determine or predict what the products are going to be. All right, so again, they're going to do-si-do. Potassium's going to go with nitrate. Barium is going to go with hydroxide, okay? So potassium is a +1. Nitrate is a -1. So when you whoop them, you're going to get KNO3. Barium is a 2+. Hydroxide is a 1-. When you combine them, you're going to get BaOH parentheses 2. Okay, so let's look at potassium nitrate. Well, we should probably know that nitrate is always going to be soluble no matter what it's bonded to. So this is soluble. So one of our products, potassium nitrate, is soluble. Our second one is barium hydroxide. Hydroxide is typically not soluble, but it is bonded to barium, and barium is an important exception. So when barium bonds with hydroxide, it causes it to be soluble. Okay, so to answer the question, will a precipitate form when these two solutions are mixed? The answer is no, because both solutions or both products will be soluble in water. Okay, so that's how you use the solubility guidelines, and that's what you do with a metathesis reaction. It's a do-si-do. You switch partners and use the solubility guidelines to determine if a product will be soluble or insoluble. Now, when it comes time to do the second part, we're going to be breaking these molecular equations down into smaller bits. And so we'll do that tomorrow. I'm going to end this video and hopefully splice the two videos together because of the technical issues. So I will talk to you all tomorrow, and hopefully, fingers crossed, this all works.